vibration rotations. Then we will move on to the Raman Spectroscopy and the electronic spectroscopy later. Then we get through our initial process. 13th September, Anuj.
किसका बर्थडे?
Whom we shared with the 1947 Nobel Prize winner, Robinson. Now, Robinson, when you do more of natural product chemistry and synthetic organic chemistry, you hear this thing very often, Robinson and so on. He was, in fact, one of the outstanding natural product chemists. He done a lot of work on alkaloid chemistry and heterothermal chemistry, and for which he got the Nobel Prize in 1947. And you will see his name over again whenever you study natural product chemistry. So 1947, Nobel Prize winner Robinson shares his birthday with us. 14th September is Ayush. And that happens during the birthday of Pavlov, behavioral psychology. He was the one who showed who brought forth the concept of conditioned reflections. And the reflections are not just.
Excuse me, can you just hold it and shoot for sir? There is some mistake in this.
Am I on mic? So Pavlov was a behavioral psychologist. He was the one who showed that you actually condition reflexes. I think the famous experiment was the ringing of the bell and providing the food for the dog. And after a certain point, the dog, the moment it hears the bell ring, thinks food is available, it starts to salivate because it's ready to get sort of have its meal. And that was a conditioned reflex that he was talking about. And he showed for the first time that the reflexes need not be spontaneous, they can be actually conditioned, which is I think the whole basis of practice. In sports or in any other art, when you practice a lot, it is simply to provide the conditioned reflex so that you are basically prepared to respond to a situation. Give the example of cricket, frozen fingers. Don't look at the ball and then decide what to do. They just do it. And that's because they have conditioned themselves to doing it. And that's basically what Pavlov has. He showed the whole concept of conditioned reflex, 14th September. 15th September, Sandra. There are two people I picked out. The two people being one of the quantum mechanics was Klein, and you see a lot of Klein's work, Klein-Gordon equations and so on. So Klein was an outstanding quantum physicist, and a lot of his concepts are used in understanding many of the properties of chemical substances. So Klein was again Nobel Prize winner. 15th September. Another great person born on that day was a very old engineer from India, Viswanathan. I don't know how many of you have heard of him. He was supposed to have been a very pioneering person in many of the engineering concepts. Those of you from Puri, I don't know, Karapatla Dam, I think he was the one who came up with the design. And even the dam at Banwell, Krishnath Sagar Dam. There were many new concepts that he brought in, and he was supposed to be one of the pioneering engineering minds of the country. And you Google him and you'll find plenty of information on the contributions that he has made. So 15th September, the two people, Klein and Viswanathan. Okay, so that takes care of the birthdays. Now we get back to vibration rotation spectroscopy. Just to recap what we did the other day, we remember we wrote these two equations. R branch, likewise we wrote one for the P branch, and then we said we give a generalized equation. I'm not going to write for the P branch because it's going to be recap, and I'm very sure you have these in your notes. And for R and P, you basically write this as that M actually takes on J double prime plus 1 for the R branch, and minus J prime plus 1 for the P branch. And therefore, get this. And we also said that this is the equation you will get if you rigorously take into account the fact that B1 and B0, B0 is the rotational constant for the molecules in the V equal to 0 level, and B1 is the rotational constant for the molecules in the V equal to 1 level. We have now become more sane. We have started believing that these two being two different vibration levels, the R values can't be the same, and they must have therefore different V values. We started off with this assumption that they were all the same and came up with a much simpler equation. Because essentially omega naught plus 2b J prime plus 1, J double prime plus 1. This term drops out because we assume these to be equal. Therefore, we have or we can expose this as n, where n is J double prime plus 1 or minus J prime plus 1, depending on whether you're looking at the R branch or the P branch. We will need this in a little while from now. That's the reason I written it up there. But before we start looking at that, I just want to show you a few pictures and see what sort of an analysis one could do. First, what I've done here is brought a photograph of a rotational line contour of a molecule. Of course, it's iodine molecule, and therefore, of course, it can't be seen in the vibration spectrum because iodine has no dipole. Dipole doesn't change with the vibration, therefore, you can't see it in vibration spectrum, but you can see it in electronic spectra. But in the electronic spectra, I'm seeing all the rotational lines, and the story is still the same. And if you look at it here, you see that the rotational lines start off here, they go up to this point, and then they come back. That's the reason why this place is quite dark, because it's exposed, it's a photographic plate. So it's quite exposed. The lines go up to a point and then they return. And this basically is what we call as the band head. This is one of the spectra that we got for the iodine molecule, recorded in electronic spectroscopic mode, but still looking at the rotational vibrational lines, which is what we're discussing now. And you can see very clearly why it's called a band head, because the head goes up to here and comes off. And if this is these long wavelength region here and the short wavelength region on that side, then you will call this as a red degraded head because it is degrading towards longer wavelength, and therefore it's called a red degraded head. This is a red degraded head. Actually, you see many such lines. There's one head over here, one head over here. That's the composition. Don't worry about it. Just look at this. Just look at this part, and you can see why it is called a head, because the lines go up to a point and then they start to return and you have the band head formation. If the lines are sort of degraded towards the long wavelength end or the intensity drops off in long wavelength end, we call that as a red degraded head. But sometimes you can have the whole thing going the other way, which of course is the case with the P branch form of head. And then you say that's a violet degraded head. In most of vibration rotation spectroscopy, you will not even see a head. And if you do see a head, it will most likely be a red degraded head. Very unlikely, that almost impossible that you will see a violet degraded head. But when you go to electronic spectroscopy, you will see that it is pretty obvious that in the electronic spectroscopic region, you will see all sorts of funny things happening. You will see violet heads, you will see red heads, and so on. Okay, we will just show you what the head really looks like in a photographic grade, if you were to record. Now this is the spectrum I showed you earlier, but we will look at it today in more detail. And this is essentially the gas phase infrared spectrum of HCl, which I keep saying that I hope you will be able to do so in one of your lab classes, and you should be able to record the spectrum yourself, and then go back and do all the analysis that we will be describing today. And I said that this is your the P and R branches that you see for the HCl molecule. and every line is also doubled up because of the isotopic composition. Now if I go, that's your R. Why? Because that's my long wavelength, high energy region, and this is my low wave number region or the lower energy region. So that's your R head, the R branch, and that's going to be your P branch. Because R and P branches, and you can see somewhere in between, the gap is quite large. The gap has to be approximately 4B, which we said is a null gap. Because what really happens is you're missing a J0, J0 transition. Simply because quantum mechanics prevents you from seeing. What I will do is the following. Let's take this region alone and blow it up. So just taking a small part, and we'll see what sort of information we can get. What is the misery we brought onto ourselves? We brought onto ourselves the issue that B1 need not be the same as B0. And we know that those two are different. So the question now is, can I, using the spectra, be able to evaluate B1? Can I evaluate B0? Which essentially means, can I evaluate the rotational constant for the lower state and for the upper state? When both were the same, all you had to do was evaluate 1B and go home. But now you have to evaluate B1 and B0. B0 is the rotational constant in the B equal to 0 state, and B1 is the rotational constant in your B equal to 1 state. And can I see both? Let's look at this situation. That's the 0 to 1 transition. That's of course the R branch, that's your P branch. Because it's the R branch, you start from 0 and goes up to 1, therefore delta J is plus 1. That's the 1 to 2 transition. That's the 1 to 0 transition. And that's the 2 to 1 transition. So you have recorded this. You also know the frequencies of each of these lines, which I have written out here, which of course you get from your spectrometer. So this line occurs at 25, 2903, 2905, and all that. So you know that. So you can actually measure it using a spectrometer. What information can I get out of this? Look at this difference between these two lines. How much is that? It's 40.6 wave numbers. That's an experimentally measurable quantity. It's 40.6 wave numbers. But then what is that also going to be? It's going to be not 4B really. This is B equal to 1, J0. This is B equal to 0, J0. And that transition, mind you, is what? Is the difference between a 0 to 1 and a 1 to 0. What is 0 to 1? 0 to 1 is this transition. And what is the 1, 0 transition on the other side? It is this transition. And experimentally I can measure the difference in frequency between those two. But what's the difference in frequency between those two going to be equal to? It's going to be, what is this going to be? This 2B0. And what is this going to be? 2B1. So this minus this has to be of course, when B1 was equal to B0, it was this 4B. But then I'm now going to use the full data with rigor. I'm going to say that B1 is not equal to B0. And under those conditions, this difference between this line and this line, which is 40.6 wave numbers measured experimentally, must be equal to 2B1 plus 2B0. Let's look at one more line. Let's look at this, which is the difference in frequency between 1-2 transition and the 1-0 transition. What I'm doing here is I'm very smartly keeping the lower state the same. So 1-2 transition is what? 1-2 transition is this. And what's the other transition? In the P branch, it's the 1-0 transition. And what is that going to be? Is this. So the difference in frequency between the 1-2 transition and the 1-0 transition will be equal to? Yes, because this we know is 2B, this we know, this difference is 4B. Alright, there you go, we know that this guy lies at 6B1. Therefore, this difference here has to be 6B1. And therefore, that 60.5 wave numbers is actually a measure of the B1 value. It's actually 6B1. So once there is 6B1, I know what B1 is. B1 is 10.08 wave numbers. So in spite of bringing in the complexity into the problem that B1 and B0 are not going to be the same, it turns out that this spectrum has enough information in it to give me the values of B1. How do I get B0? Well, you already know that 2B0 plus 2B1 is this much, and I know what B1 is, therefore I know that. But in science, it's not, you just don't take two values and be done with it. You try to do multiple estimation of that number by taking various quantities and getting the same number over and over again. And if you do that, that's when you are absolutely sure that you have the right numbers. I'm not going to describe that now, but go back and see how Raleigh and Ramsay discovered inert gases. They simply measured nitrogen density by 2 or 3 different methods and found they were not agreeing. They were measuring the same nitrogen by 2 or 3 different methods and found that they were not agreeing actually. The numbers were different. And different by how much? By 0.5% or 0.2% and so on. Most people would have said that's an experimental error, I can live with it. But not Raleigh and Ramsay, because every time they did the experiment, they got that 0.5% difference. And they said that must be something. And attributed that difference to the presence of an inert gas. And that's how they discovered. So any time you try to get numbers, always get multiple observations and then decide on the veracity or the validity of that number. So right here you can get B0 and go home, but that's not the way you do it. You try to see whether I can do something else. Take these two differences. And what is that? Is the difference between 0, 1 and 2, 1. And what am I doing? In this case, I'm keeping the upper state constant and I'm looking at two transitions which have the same upper state. In this case, these two transitions have the same lower state. In this case, I have two transitions with the same upper state. And there are 0, 1 and 2, 1. So 0, 1 and 2, 1 would be this and this. And this number, the difference, which I know as in 62.5 wave numbers, will be equal to B0, which is what that is, and therefore B0 is 10.42. If B0 is 10.42, go back and see whether 2B0 plus 2B1 gives you 40.6. Not going to give you 40.6, but it should give you something close to 40.6. Because there's something called statistical errors in your experimental measurements. And also how well you have measured these frequencies. That's very, very important. So to the level of accuracy that your instrument can give you, these numbers should agree. Actually it turns out that well. I think you get, when you add these two, I think you get 21 or 20 or 40 point. Yeah, I think 41. You get 41. 40.6 and 41 is within the limits of accuracy that this machine can give you. And therefore, that's consistent. But what have you done in the process? By simply looking at 4 lines in that spectrum, what you should really be doing if you are a professional spectroscopist is take many more lines and keep getting this B1 value over and over again to multiple measurements and multiple estimations and see whether these numbers are going to be the same. What do you think will happen if I start going to lines way out and start measuring my B1 value? Will they still agree or will they not agree? Let's say I go to J 10 to 11 or 11 to 12 and start getting those differences. What do you think will happen? Do you think I'll keep getting this number around this value or will that be different? Why will it be different? Yeah, the centrifugal distortion term comes in. And if I don't, this analysis does not take into account centrifugal distortion. So if I go to very large J values and try to estimate my B from there, no, it will not work. So what do? You take the equation with B and D and then go linear least square split and then get your B values and D values. I'm very sure in your IDC you have been taught how to do least square splitting. This is a good example of how you can use least square splitting and get your B values, D values and so on. In this case you don't need least square splitting. You can actually estimate this from kindergarten arithmetic. But then if you want to be using this long expression with B, D, H, L, and all these centrifugal distortion constants and so on, then you will have to do a least square split and get all these parameters. That's the way you do it actually. And then you do that, you get good values for B, you get values for D, and so on and so on. With this analysis that we have done, we have got basically B1 and B0 and H1. And you can see, we said earlier, when we analyzed this equation for the P and R branches, that B1 minus B0, we said the B1 value must be smaller than B0 because B1 is for the upper state, the higher vibration state, which has longer extensions and therefore longer values of R, and therefore the B1 must be smaller. Well, that is consistent. The B1 is in fact smaller than the B0. So the whole analysis is quite meaningful. Yeah.
Let's say put an imaginary line, J0
Yeah, I
Are
know.
you?
Okay.
I'm not able to understand how that 6B1. It will be 2B1 plus 4B1.
Which one?
The top line.
This one.
Sorry, 2B1 plus 4B1.
This one.
The top line.
This one.
Yeah.
No, I have kept the ground state the same. Look at this one. Let me make it simpler by erasing out all the things that I don't want. Look at that. It's 1, 0, 1, 2. You're talking about this level, right?
Yeah.
Okay. It's a transition going from 1 to 2 to 1. This is the 1 to 2 transition, and that's the 1 to 0 transition. So 1 to 2 transition is this, and 1 to 0 transition is this. So if I take the difference of these two, the B0 will not show up because I'm using the same lower level. But here it will be this difference is 2B, this difference is 4B. Therefore the total is going to be 6B. Have I made sense? No, it's not equal space. Take J into J plus 1. Here is 0. Here J into J plus 1 will be 2. Here J into J plus 1 will be 6. That's why it's simple. So in fact what you really do is you very smart, you take one of these states to be the same. Here I have taken the upper state to be the same in this case. But I get B not value.
But the spectrum will be equally spaced.
Well, the spectrum will be equally spaced if spectral distortion doesn't come in. Yeah.
That's why we don't take the distance between two of them and one side and this way it goes.
Yeah, if I take these two, let us say 0, 1 and 1, 2. If I take this line, you can work it out, see what you get. That's my 1, 2 transition. It is this level. And the other one is the 0, 1 transition. So this plus 2B1 equals this plus 2B0. So both 2B1 and 2B0 will be involved in that expression. So I know this and this. So basically I'm going to get the estimate of this and this together. But if I use one level to be the same, then I'm basically removing one of these constants from the picture. And therefore I get it simply as it. But you could do it this way. I mean, you can use different sets of levels and solve simultaneously for B1 and B0. Actually, you could do many things. You could basically take different combinations. And you must, as long as you haven't gone to very high J's and messed up the thing with the introduction of the centrifugal distortion, your B1 and B0 values, doesn't matter what combinations you take, they must be within the limits of experimental errors. And within about half a wave number or so, you must get it. We will try and set this experiment for you. And I would really like it if you use your imagination and came up with all sorts of combinations and estimated B1 and B0 for the HCl molecule at that point in time. So that's basically what you would do, and then if you went on, that's my 2B0 plus 2B1. From this, we'll estimate this to be 41 wave number, but experimentally I see to be 40.6, within half a wave number, which is the experimental uncertainty that I will estimate these experiments, therefore it's perfectly fine. You saw each line is doubled up. This one is 2905.8, this is 2903.9, and what does this do to the HCl 35? I can actually estimate what the frequency of HCl37 would be if I knew what HCl35 was. And how do I know that? Because mu for 35 equals 1 over 2 pi 2 tau k by mu for HCl35. And mu for the 37 isotope is again 1 over 2 pi. What about the two Ks? Will they be the same or different? They're the same, because I haven't changed the number of neutrons. There's really no need to believe that these, at least in the first order, are going to change any of your force constants. So the force constants are the same, and therefore I can get an estimate of these two frequencies as simply being the ratio of these two. If I just divide these two, I'll basically get the ratios in terms of mu 35 and mu 37, the square root in between, and that's what I've written out here. So if I know the frequency for 35, which is this, and I know the reduced masses for HCl35 and HCl37, then of course I can estimate what the HCl37 vibration frequency would be. And if you do that, go back and evaluate this, and these evaluations you must do. Get your numerics update. When you do this, you can evaluate what this is going to be. It turns out to be the whole square root term will give you 0.9992 into HCl frequency at 35. Therefore, if it is 2905, the HCl37 must be at 2903.5. When you calculate this way, then you go back and see it's 2903.9. What 0.6? That's perfectly fine. So you get the assignment that this must be due to the isotope. Instead of HCl35, if I do BCl35, for HCl35, then instead of making the HCl37, I replace the hydrogen with a deuterium. So therefore, I am not replacing the chlorine isotope, I am replacing the hydrogen isotope to a deuterium. So it's heavy HCl. And you can prepare heavy HCl and do these experiments. And when you do that, see what happens. There is a big change in the reduced mass because you changed A to B. You have replaced 2 with 1. It's a huge change in terms of percentage change, relative changes. Therefore, you will find that this term actually will be 0.5139. Therefore, this 2905.8, if you were to find out what the frequency of that 1-0 transition would be, 0-1 transition would be for the DCl molecule, where is that going to be? 1493. It's going to be out there somewhere. Way out. In other words, there's a huge shift in the frequency whenever you change the lighter isotope. That's the reason why when you want to see big changes and you want to make sure that this frequency is really big.